and adding the res and the mid index plus 1.
Mm-hmm. Yeah, totally.
Yeah, that's like we're
That.
trying to break it down and go through it step by step, and we were having trouble, so.
Let's do it with the whiteboard to start with. And I pulled out the screws, so now I won't have anything like poking into my legs and stuff. So I'm super stoked about that. My wife finally made me clean up this room with her help. She did a lot of it too, but she was like, "It's time to clean." Yes, Kevin Wong, I am recording. So everybody forever can hear that impression of my wife. All right, so let's say we've got this array. Remember, so binary search only works with what type of sorted array? Sorry, with what type of array? Did I say it? Did I say
You
it?
said it.
Yeah, that's what confused me.
Sorted array.
That was the trick right there, man. Like,
Okay, my bad. All right, this is my warm-up. I haven't had a lesson yet today. So it only works with a sorted array, right? So we got to remember, like, it's sorted in some way. So if our data is sorted, binary search is a potential option or a potential tool for us to use. If the data is not sorted, we can't use that, right? And that's just sorted in some way. It doesn't have to necessarily be a non-decreasing order or decreasing order, right? All right, so let's say I have 12, 13, 14, 15, 16, and 17. Okay, so this is my array. This array is sorted. And let's say we are looking for the number 12. We'll start off with a left side. Or does anybody have any issues with the left side concept or no?
All sides.
Ashia?
every single side.
All sides.
Okay. So, okay. So our binary search, we are looking for, if it's an empty array, we know that we have not found our item. Is that fair?
Yeah.
Okay. So let's say we're looking for 12. So we'll start with the easier side first. Okay, so we have this array length. So it's 1, 2, 3, 4, 5, 6. Now, the middle of this, is 6 divided by 2, right? That's going to give us our 3. So let's go to that third index. So we have 0, 1. I'll do little numbers underneath. Keep it easy. So we go to our third index and we check this 15. And we see, is 15 our 12, right? Because we are looking for 12. What is it? Is 15 12?
No.
No, right? Okay. So does 12 exist? Well, like, you don't have to look at this, but does 12 exist on the left side or the right side of this 15?
The left side.
On the left side.
Right. It has to, because this is an ascending order, right?
Mm-hmm.
So we know we don't care about anything to the right of the 15. It's irrelevant. So we're gonna make a recursive call on the left side here. So 12, 13, 14. 0, 1, 2. Right? And we're still looking for our 12. But this is our new array. So we look at the middle. We look to see if it's empty, to see if we haven't found it. And it's not empty. So we might have it in our array, right? We don't know. So we have to find the middle index. And so we're going to look at our length. Our length is 3. And we're going to divide that by 2. And we'll round that down. So we get 1, right? So our mid index is our 1. So we're going to be looking at this number right here, right? Our 13. So our 13, is that equal to 12?
No.
No.
No, right? So what side of the array are we interested in exploring?
Left side.
Left side.
Left side, right? Because we know for sure it can't be, we don't care about the right side because 12 is less than 13. So we're going to call our bsearch function again with our left side of the array. So I'm going to say 12. And so this is our new array, indice of 0. It's not empty, so we know it's not, like, we haven't not found it yet, right? So we're going to take the middle. So we say 1 divided by 2. and round that down. So we're going to look at the 0th index, which is right here. And here we say, all right, is 12 what we're looking for?
Yes.
Yeah.
Yes, right? So we are returning this index of 0 because that's what we care about in the binary search in this case. So our 0 bubbles up to this next call because this is just returning the left call.
Mm.
And then since this is returning this left call, it keeps returning all the way up, and our function will return the 0. Okay, any questions on that, on the left side traversal?
This is bubble and sort, no?
No, this is binary search. Bubble sort is where things swap positions
Oh yeah.
from the largest thing all the way to the end. Binary search only works if the array is already sorted.
Okay. Yeah, exactly.
Okay, so Ashia, you asked this question. Any questions on the left side, or does this part make sense?
Okay, so like when it starts bubbling up, I think that's when I get confused.
Well, that's just recursion. That has nothing to do with binary.
Okay.
So I can answer that, but that's not really a binary search related question. That's like me saying I want the factorial of 5, and this is going to be whatever the factorial of 4 times 5. So that's like saying 5 times fact 4. But this hasn't resolved yet. So it goes down and it says 4 times fact 3. And that hasn't resolved yet because that's still calling a function. So then it's 3 times fact, let's say 2. And that still hasn't resolved because this is still a function call. So 2 times fact 1. And we'll say, okay, this has resolved, let's say. That just becomes a 1. So I'll cross that out to be a 1. So then this function call resolved to 2 times 1. So that's 2. So this essentially becomes the 2. And so then 3 times 2, this can now resolve, and it bubbles back up. So now this is a 6, right? So then we have 4 times 6, and then that can resolve and bubble up. So we have our 24. This becomes, 24. And then we have our 5 times 24 finally, where it gives us back our 120, which is what the answer is, a factorial 5. So that's just how recursion bubbles back up after it's gone all the way down. And like a real life example of this is like, let's say you were sitting in some random row of a movie theater and you didn't know what row you were in, right? But it was a full house. So you tapped the person in front of you and you said, hey lady, what row are you in? Because you know that whatever she answers to you, you're just going to add 1 to that, right? And then you'll know what row you're in. But what if she doesn't know what row she's in? So she taps the person in front of her and she says, hey, mister, like, what row are you in? And he goes, I don't know. Hang on. So he asks the person in front of him, right? Now that person, they are in the very front row. So they know, like, they're row number 1. There's no need to know, right? You know if you're in the front row of a movie theater. So then you would just answer to them, well, I'm number 1. And then the person behind them would go, oh, okay, so that makes me 2. And then tell the person ahead of them, behind them, well, I'm 2. So that person's like, okay, well, then I'm 3. Right? So that's how recursion bubbles back up. Does that make sense?
Yeah, we were trying to visualize the return statement of res equal -1, if res equal -1.
Yeah, so that's the right side of binary search. So I hear you. We got to approach these really specific, or we're going to get confused. So we have to understand how bubbling up of recursion works. If we don't understand that, there's no point yet going to binary search because it's going to be a little bit more complicated. We did the left side because it was the immediate index that we want. If we're tagging the right side, we'll work on that next.
No, we were still attacking the left side. I think we were stuck when we got back to, like, say instead of 12, we did 13 instead. We got stuck on adding the res plus the mid index.
Yeah,
plus
that's
1.
part of the right side.
Okay.
So remember, if it's smaller, then it's the left side. If it is the number, it's the index. Otherwise, it's the right side. And if you look at that number, that whole res thing has all to do with the right sides. It's
Okay.
all hitting that else statement.
All right. Gotcha.
So I'm going to talk about that in a minute.
Okay.
I just want to make sure we all understand the left side. Any questions on the left side? Okay, so now let's talk about the right side, because the right side is definitely, as Ashia mentions, a little bit more complicated / well, just more interesting, really, right? So I'm going to call B search on this array, and we're going to look for 17 today. Okay, so we're going to first have our mid, because we know it's not empty, right? And our mid, we said, gives us back a 3, right? Length of 6 divided by 2. We'll say our mid is 3 here. Now, so we're looking at the 15, and we're searching for 17, we'll say. Is 17 on the right side or left side of 15?
Right.
Perfect. That's right. Okay, so we have to look at the right side. So we're going to grab this array, and we'll say 16 and 17. Now the indices of this array on this new call is 0 and 1, right? Because that's an array. And so we've called B search now on this array. Okay, so we have an array length of 2. 2 divided by 2 is 1. So we're looking at 17 in this case scenario. 17 is equal to 17. What does this return?
70.
Well, the index is 1.
Right, so this returns 1. So B search on this array evaluates to the number 1, correct?
Yeah.
Okay, so in our left side, we were able to just return whatever we got back from B search. But we can't do that on the right side because we're returning the number 1. But 17 isn't the number 1 index. It is for this miniature array we sent back, but it's not for the real array, right? 17 is index 5.
So do you need to concat?
No, there's no concatenating because we're just trying to keep track of the index.
Mm-hmm.
Right? Concatenating is we'd be building this array.
Okay.
Instead, we're just trying to figure out what the original index is. And so we can see that the index we're looking for is 5. But when we looked at the right side of our 15, we got back this index 1. Well, can anybody tell me why we're getting 1?
Because
What's the end? Oh, sorry. Go ahead, Martin.
no, you got it.
No, you. It's all you.
Because in the miniature array, 17, index 1 evaluates to the number we were searching for, right?
Right, and which is 1, right? But so how can we actually do this, right? That becomes the question. Well, we know when this bubbles up, this is giving back a 1. So we still have this mid-index to help us guide how large the initial array was before this call, right? So we can add 1 plus 3, which is the mid-index, and we'd still have 4, right? So we're still 1 off right now because we really want to have 5. So who can tell me the reason why we're 1 off right now?
Because we starting with 0, so that's why like we have
In
to.
this one, right?
Yeah.
Exactly, because the new array has its new indices starting at 0. So we're essentially dropping the possibility of counting this one, right? So instead we're just counting this one and the mid. So that's why we're adding that extra 1. That's why it's res plus mid plus the 1. So this 1 is making up for this 0 in the array. This mid is making up for the middle point of the array call before. And then the res is the actual index that we're getting back. Now, the reason we're checking if it was -1 is because -1 means we went through the array and did not find the item we were looking for. And so we don't want to keep adding the mid and 1 to -1 because then we would have some number. Like if I looked for 18, right here, let's go ahead and pretend I'm looking for 18 now instead. And I look at my 1 here and I go, okay, it's my mid index. My mid is 1, right? And 18 is on the right side of this. So I call B search on an empty array, right? Because this is everything to the right of our 17. And I would see that this is empty. So this is going to evaluate to -1, right? Are we with me so far?
Yeah.
And it's empty evaluates to -1.
Right. Because that means we didn't find it. B search is returning -1 if the target element is not in the array.
Okay.
So empty array means guaranteed it's not in there. So we can go ahead and return -1. So now in the bubble up, we don't want to add 1 plus our mid plus 1 plus our response, because then we would have a 1 here. That would be 1 plus mid, so that's 2 plus -1. So then we would have this response of a 1, and then we would keep going, and we would have 3 plus 1 plus 1, and we'd end up all the way up here. We would see we had a 5, and we're like, well, the index isn't 5 because 18 doesn't exist in the array. So in order to make sure we're not adding onto a -1 answer, that's why our right side is checking, hey, if our response is -1, go ahead and keep returning -1. Otherwise, go ahead and do the math of taking that response, adding it to our mid, as well as adding the lost 1 from the indices starting at 0. Okay, and that is binary search on the right side.
So quick question for you.
Uh-huh.
If that array was 16 and 17 in it, and let's just say we were looking for 17, 18, 19 or something like that.
Yeah.
And we would end up creating a new array. So what would the mid be then?
Well, if we were looking for 19, it would be the same thing. We would have gone for the right side of 17, which would have been an empty array, and it would have given back -1.
So, well, let's just, I don't know. I just named some numbers, but let's just say there's a scenario where we have to make a new array after going to the right side, I guess. And
what do you mean by make a new array?
So from the first array, we looked to the right side of 15.
Yep.
And we created that right side array with 16 and 17 in it.
Yes.
Let's just say there was 17, 18, 19, 20, 21. And
we want more items in here.
Yeah, more items in the array.
Okay. 17, 18, 19.
Right.
Okay.
And so now we're looking for 19. The middle is floored to 1. Floored to 1. 1 or 2, whatever. And then we have to go to the right side again.
Okay, so you want to keep looking for 19, no problem. So we'll say this is 4 items. So our mid is 2. And so we look at the 2, and that is our
Mid.
that is our mid right here, right? 18 is less than, we said we were looking for 19 now. Is that right,
Mm-hmm.
Danny? Okay, so we're looking for 19. So we got to go to the right side of there. So we are going to call B search now on an array with 19 in it. Our middle will be 0, which is our mid, and that is in fact our 19, right? So this is going to return 0, right? Because this is the 0th index, and it found it. Are you still with me?
Yeah. So once it returns 0, the function, the entire function is supposed to just stop.
Well, then it has to bubble back up because these have been recursive calls. So 0 plus 2 plus the 1, because we have our response is not -1, so we care about it. So 0 plus 2 plus the secret hidden 1, that gives us back the index of 3. Okay, so now we have a 3 here. We should add 18, 19 up here. So 6, 7 is our goal. 3. And then when this evaluates to 3, this is not -1, so we want to do our math. So we go 3 plus 3 is our mid, plus that hidden 1, which gives us back 7. And 7 is the correct index.
Okay.
So it still works.
So essentially, like when we're so in this scenario, we would have 2 base cases.
We would just have the one base case, which is if our array dot length is equal to 0, we can go ahead and return false.
So that's the only base case?
It's the only base case we'll need. Then we'll find our mid. If array at mid, if array at mid equals our target, we return our mid. If our array at mid is greater than the target, then we can just go ahead and return the left side. So if array at mid is greater than target, we can return our B search on our array, where we can slice from 0 to the mid. And we can safely return that because the indice doesn't change as the array shrinks. The 0th index always stays the 0th index, no matter how many times you cut that in half. It's the right side where we lose. So else, we have to save it as a result. So we have our result is equal to our B search of our array at slice of mid plus 1. So we can go ahead and take the right side and save it. So if this response is -1, if res is equal to our -1, we know we didn't find it. So we can just keep returning -1. Otherwise, we need to return our res plus our mid plus 1.
So we're calling B search on in our for res, we're calling B search on the array to slice it at our mid plus 1. And we're doing that because our previous mid, we don't need to include it because we know that it's not the number.
That's correct.
Okay.
That said, everybody, you will not be asked to do a B search recursively. You will be asked to do a B search. You can also do it iteratively. Iteratively is a little bit more straightforward. It's not quite as pretty necessarily. It's pretty similar though. And personally, I think the iterative one is a little bit more intuitive. But
If we know the recursive one better, is it okay to do the recursive one?
yeah. But definitely familiarize yourself with both. You could be asked to do both in an interview in real life. Does that answer your question, Ashia? Does that make sense?
Yeah.
Okay. Awesome. That's great. Next question.
So, for me, I don't know what I was supposed to do in one of those problems, but I just noticed that when I approached it whatever that word is.
Iteratively.
That word.
Yeah.
I just felt like it was too much redundant code, and it was just like a lot for something that I felt should be simple.
Should we talk about the problem?
Yes, it was the merging the arrays.
Merging arrays.
The sorted arrays and returning a new linked list.
I think that is actually merging two linked lists.
Linked lists. Yeah, it's two linked lists.
Okay, so yeah, we can talk about this one.
Yeah, when you're doing, like, when you're trying to test it, how do you set up the linked list when you're when you actually do the console log?
So that was a leak code problem. So it's already all made for you. They've set up all the tests.
No, we were trying to do it on Replit.
Yeah, but that's part of your issue, perhaps. I mean, you could definitely make your own linked lists and write them, but typically, I mean, leak code's already got all the tests built for you. There's not really any point to practice it on REPL instead of on leak code.
Okay.
So my suggestion for that would just be to actually do it on leak code. You can build it. You know, you can build a linked list on REPL, but you might as well do it on leak code because they already have all the test cases for you.
Yeah, like for me, I spent a long time on getting it, and then I just I got to like the last test, and I just realized that I was doing way too much, and I know for a fact that it can't be that much code for this problem.
Okay, so this kind of problem, I should say, is a very common problem. You see it in arrays and linked lists. So we've already done it once with arrays, right? As part of our merge sort day. Do we remember that?
Yeah.
Yeah.
Okay, cool. And so, and I want to just make sure I have all the questions open for this. Let me just take a second to make sure. Let me just copy the practice test over. Okay. To my notes so that I can better find them because I don't like reading them in a certain way. Let me see. Practice test. Okay, great. All right, so this is our problem. So when we're dealing with this problem, what do we like? How do we go about thinking about this? What's some of the approaches that we may have tried?
So my first approach, just looking at it, was basically iterating through each linked list.
Okay.
And just checking the current node with the current node from linked list 1 and the current node to linked list 2, and checking to see which one is greater, and then adding them accordingly to the output linked list.
Great. That sounds like a great approach, and I'm surprised that might not have been working. Let's let's try it.
Worked
So,
until like it worked until I got to certain points of the test and I just couldn't like smoothen them out.
well, that's all part of practice. But yeah, let's go over it. So let's say we have we'll call this output list, right? And so if I want this, I can go ahead and make a new list node, right? So this is just going to act as a dummy node so that I have a list to append to. So the code is very similar to the way we had it with the arrays, I think. So we should be able to say something like, hey, while we have an L1 and we have an L2, so while we have these nodes of both, we can go ahead and take a look. So we can say, hey, if L1, L1.val, right? Because we know it has a value property and we know it exists. So if that val is less than our L2.val, what would we want to do?
Add that val to, or create a new, or add the val to the dummy node that we created.
Yeah, exactly. So we can say output.next, and I'm going to point that to be our L1. That's that now node. I'm also going to keep oh yeah, thank you. I'm also going to keep track of a current instead that's just going to point to my output. And so that way I'll have this at the very end still. And I'm going to actually make this current.next. You'll see why I'm doing that at the end. It's because I'm going to be traveling along the whole time. And I don't want to lose track of the head at the very end. So we'll say, hey, else. Well, then we just have to say current.next. That should equal our L2. Okay, so now our next node, we're saying, is equal to whichever one of those is smaller. And then at the very end here, I should increment my current is equal to current.next. Now, in addition, I still need to travel along our L1 and our L2, depending on which one I chose. So if I've determined that my L1 is smaller, I should also go ahead and re-update my L1 is equal to L1.next. And if it's the L2 that's smaller, I'm going to go ahead and move that one up as well, L2.next. Now, I should be able to assume that our current is going to make it to the end, but they could be different lengths. So one of these still has something left to it. So I'm going to say, hey, if L1, just going to say current.next is equal to L1, else if L2, current.next is equal to L2. And at the very end, I'm going to return my output, but my output started with a dummy node. So I actually want to return output.next. And I'm hoping this will work. I'm not referencing anything, so we'll see.
Well, you need to change your values for the current.next. Don't you need to change it to the value?
It's supposed to point to the next node.
Okay, yeah. Actually, yeah, you're right.
So let's see if this works, and then we'll start debugging together. Okay, so I have a runtime error. Current is not defined, misspelling. Okay, let's run it again. This one looks like it's accepted. Let me go ahead and submit the code. And it works. Awesome. So let's go over again what this code is doing now that we are certain that it does work. I haven't solved it for a couple of years. Okay, so we are creating a dummy node to start with the linked list. And we're also keeping track of a kind of a pointer to help us traverse through this list as we're updating it. And we take a look, hey, while we have two lists still that have active heads, we'll just do a little check. If my L1 value is less than my L2 value, then my current.next will point to my L1, and then I'm going to update my L1 so that I'll have it for the next iteration. Else, I'm going to point my current.next to be my L2 and update my L2 so that I have that new L2 for the next iteration. Regardless, one of these two things happened, so I'm going to update my current to be its next, so we can then keep assigning its next to be the next node. At the end of this, I'm going to make the assumption that our linked list may not be the same length, and so one of them still has some leftover nodes. And so that's what these are handling. It's saying, hey, if I have an L1, I'm just going to set my current.next to be that L1. Otherwise, if I have an L2, this really could just be an else statement, but our current.next will point to our L2. And I don't need to continue to traverse through these because they're already sorted and linked up. So I don't need to like keep linking them. And then I'm just going to head and return my output.next because I don't want to return this fake node that I created to act as a head. I want to return only the nodes that were in the original two lists. Any questions on this?
So that conditional from lines 26 to 30, that's pretty much in case like there's any other like nodes left on these lists because we don't know how long they are, right?
Right. So we're pretty much guaranteed to have something. So like if we walk through this with 1 and 1 here, right?
Mm-hmm.
We hit our else statement and our current.next points to this 1, right?
Mm-hmm.
And so let's say now this has 3, 4, and this has 1, 2, 4. Then we add our 1, and we have our 2, 4, and our 3, 4. Then we add our 2, and we have our 4, and our 3, 4. Then we add our 3. So now we have a 4 and a 4, right? We have two lists with a 4. And then we add a 4. And now, since that got updated, one of these is null, and the other is a node with 4.
Mm-hmm.
And so this while loop breaks because we're guaranteed that one list is going to finish before the other. We don't know which one,
Right.
and that's why we have to do this little check to see which one. But we are for sure know that one of them has something left.
That makes sense. And then you just grab that one.
So then we're just checking whichever one of you's got something. Go ahead and
add it again.
Right? Because even this list could have had more, 5, 6, 7. And then that would have been fine because we would have just added the 5, and the 5 already points to the 6, which already points to the 7.
Yeah. All right, makes sense.
Cool.
So, all right. So once the while loop breaks, and so on line whatever 22 or 18, whichever one fired, once it breaks, we essentially reassigned what L2 is or L1 is, and now we're saying that it's the next node. And then when
talking about these lines or which lines?
Well, I was just speaking from the point where it breaks. So if we hit one of those, so if the last conditional we hit before it broke was like line 19, we reassigned L1 to L1 dot next, right?
Yep.
So now we're saying on line 26 through 29, we're saying if any of these are left over, then our current dot next is going to be whatever, if it's L1 or L2. But
yep.
what if like, so essentially, like, isn't L1 still the original list?
No, we are actually pointing to these nodes. This current.next literally points to L1. And then our current in the next iteration literally is L1, and I'm changing its pointer.
Oh, okay. So what if there's multiple nodes left?
Won't matter. They're already sorted, And so they'll still continue to point to each other.
Oh,
Only one list will have nodes left.
yes.
Otherwise, our while loop will never break.
Okay, I get it.
That's a good question.
Yeah, I did it like what I did was kind of crazy. I was comparing the two. I created like a whole I did a lot.
Yeah, I mean, so you should attack these problems like this is pretty much the same as that array, the two sorted array problem. It's just with a slight twist, right? But it's the same type of logic with the while here, and then instead of pushing, it's just current.next, and I'm updating my current. And then here, it's just instead of doing the concatenating, I'm like concatenating I'm just assigning any nodes that still exist to be left with that output.
Yeah, what I did for my while loop was I didn't say if both of them exist. I said if L1 or L2 exists, and then I accounted for.
And then you have a lot more conditions in your.
Exactly, I had too many.
Yeah, that's feasible to write it that way, but you'll definitely be shooting yourself in the foot a little bit.
A lot. I had every issue.
Yeah. Okay. Any other questions on this problem from anybody? Okay, then I'm going to stop share. What other questions do we have today?
So for some reason, I'm a little stumped on the problem that involves finding the letter that appears most frequently. But can I share my screen to sort of show you?
Absolutely. I feel good. No, 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 no.
Everybody see? All right. So this question is the one that returns the letter that appears the most times, right? So I started with I made a count, and I made a count. I did my normal count. If it appears, at one, if it doesn't only appear once, then set it to just one. Now I'm sort of stuck as to sort of just how to get the key inside of the value, because now I want to get the key that's associated with that highest number.
Okay. So I'm a little confused by why we're pushing anything into this keys array.
Oh, that was just something I was trying. I just wanted to get all the keys in there, and then I wanted to make some kind of like comparison to be like, if the count at this key happens to be equal to like I wanted to make a comparison between the key that's inside of like the count thing, because that would have like an association with the value for that key, and then the actual key itself. And then somehow out it to be like, okay, cool. If that key equals 2 in the count, that's the biggest count, then return that key. I don't know. I wanted to make some.
Okay. Do we know how to get all of the keys? If these are supposed to be the keys in the count object, is that correct? Yeah. Or am I mistaken?
No, you're right.
How can we get an array of keys from an object?
A set, right?
No, there's a command.
No, that's an object.keys, right?
And object.keys, and then you pass in the object that you wish to get the keys from.
Yeah.
And then you would already have an array of keys.
Right. I guess I was confused as that, because I guess we needed to make some kind of comparison with that value, with which had the biggest value. So I was afraid I was going to lose those values in some way.
So that doesn't mutate your count object, so you still have access to that.
Okay.
Throughout, which is what you're doing, ignoring how you're getting that keys, because that's not right. But once you're iterating through and you're iterating with this key, I think that's a pretty cool approach where you're saying, hey, count at key. If that's bigger than my biggest count right now, right, then all you have to do is save that new count and save that highest letter.
Oh, okay. So I got the keys in the wrong way. I just forgot object.keys, and then I can just continue going with this. So I'm in the right.
That's right.
So all right.
I'm going to walk through this problem though now.
All right. So let's actually do this object.keys. Why did I push that here? So I can actually do I can actually still do object.keys inside of here, right? Or no?
Well, why don't we just do object.keys right before the for each?
Right before the for each.
That way we have our array.
Right. Right about here.
Like literally, instead of calling it on keys.
Yeah. Right. Object.keys, right? Object. And then you invoke that and you throw count inside of there.
Okay, sure. And then that would be array.forEach instead of
keys.
key.
Let's call them that. And then if count, my key is biggest count, then I would save the highest letter to be that actual key, right?
Yep.
So,
Okay. Let's do that.
Key. And then biggest count would just be the count at the key, right?
That's right.
So biggest count.
Okay. And then your return at the end of all this, what instead of returning count, which is the object, what would we like to return?
We'd like to return that key and that letter, actually, that key.
Mm-hmm.
Highest letter.
Perfect.
Okay, awesome.
And let's go ahead and test this together.
So, no, sorry, the screen share menu is always blocking my thing.
Oh yeah, I hear you.
T, okay.
You get T.
Okay.
Awesome. Does anybody have any questions on Marvin's code?
All right, I think we're good. Thanks, Corey.
Okay, yeah, no problem. Thank you, Marvin. You were very, very close.
Yeah, I guess I was just like, I was so worried. I was like, oh man, if I need to have access to the keys, but I don't want to lose like the values. And my brain completely forgot object.keys. I think I thought about it, but part of me was like, nah, that's not going to work. It's just going to get a bunch of keys. And then I was thinking about sets for some reason. Like I overthought it.
Yeah, another option for you would have been to use a for in loop and to just iterate through that object and look at the keys and values.
That probably would have been cleaner, actually, right?
It'd be similar.
Okay. Okay, cool. All right. Thank you.
Yeah, no problem. Any other questions at all?
Do you mind doing like a run through of like the depth search?
No. Which do you have one in particular?
So I was kind of confused with the like finding the sum but doing iteratively.
The sum of the depth first search?
Yeah.
Okay. Okay, let me just make sure I understand. Is it one of our practice problems?
It was like one of the examples that you had went over. It was tree sum, depth search, that word.
Iteratively.
Yeah, it's
sure. So you won't probably almost ever have to do a DFS iteratively. So I can go over, but I don't want that to really be the focus. When you do depth first search, you are typically doing that recursively. Did the recursive one make sense to you?
a little bit, but like when I was drawing it out, like I wasn't really connecting how like I'm going all the way down and then like working my way back up with the left and then the right side and adding them.
Okay, so we are talking about this problem here, right?
Yeah.
And your original question was on this one, is that right?
Yeah.
So this one, I'd really like this to be more of a bonus, and I don't want us to be too bogged down. I'd much rather have us fully understand how to do a basic DFS recursively, as well as a basic BFS, which is iteratively. Okay, before we get into like these types of things. So this problem, let's whiteboard it, I guess. That probably would make more sense. So we are trying to come up with this sum, right? So let's say we have a tree, Okay, so we've got our tree here. Let's make this node 13. This will be 5, we'll say 7, 2, and 1. Okay. Fair tree?
Yeah.
Okay. And so we're starting with this root node, right?
Okay.
So the first thing we're getting is we're calling DFS on this node. So we're saying DFS on this, we can say 13 here. And so we're first saying, hey, if there isn't a node here, we're just going to return 0. Right? Because the sum of nothing is nothing, we could say. Otherwise, we're going to take our current value, which is 13, plus whatever we get back from those recursive calls. So from our left child, we'll say DFS on 5, and plus I'll say DFS on 7, right? So from here, we have this node, right? We have our 5 node, and this has an evaluate. So we have to go down this rabbit hole of this function call. So this becomes, it says it's going to return 5, our current node's value, plus whatever it gets from its left side. So DFS on 2 plus DFS on 1. Okay. And so we're still haven't done this side yet. That's fine, because we have to go down. Once we've made this call, we have to go down this call. So now we're calling DFS on 2, because that hasn't settled yet. So we say, okay, well, that becomes 2 plus whatever gets on its left side. So DFS on null plus DFS on null. That's its right side, right?
Right.
And so these actually have an evaluation because they hit the base case. So this returns, this becomes 0. And this one becomes 0. And so now the call of DFS2 returns whatever this evaluates to, which is
0.
2,
Oh.
right? Okay, so now we go down the right side here of this call. And so we're now on the DFS, whatever we get back of this, which we said is the value of 1, plus DFS of null, plus DFS of null, right? That's our right side, because 1 has no children. So this actually evaluates to 0, and this one evaluates to 0, right? Because those are null. So now our DFS of 1 can actually give back a return value of 1 plus 0 plus 0. So this becomes our 1. And this gets popped off of that recursive stack. So now that these are all solid numbers, then our DFS of 5 can finally actually return something, which is 5 plus 2 plus 1. So this becomes 8. And now we have to go down the right side of 7. So this, we said, doesn't hit our base case. So we're going to return 7 plus our DFS of our left side, which is going to be null, and our DFS of our right side, which is null. Well, these evaluate each to 0 because they've hit our base case. So now that it's no longer a function call, these can go ahead and return because we actually have 7 plus 0 plus 0. So this DFS 7 can finally evaluate to 7. Okay? And that gets popped off the stack. And so now that this isn't waiting for a function call, and this side isn't waiting for a function call, we can finally return 13 plus 8, which is 21, plus 7, which is 28. And so this evaluates to the number 28, which should be the right answer. 28, yeah.
Okay. So like once you do the evaluation, then you pop it off the stack.
Yeah, well, this is happening recursively. So it's a call stack. So it's just bubbling up. It's once it evaluates to something, it's coming off of the call stack. It's done. It's not waiting for a response anymore.
Okay.
And with a depth first search, it's the search that goes down the left side first and then makes its way to the right side, right?
Yeah, I mean, traditionally. Of course, if I just switch the order of the dot left and dot right, I would go down the right side first. But traditionally, it's the left side first.
Okay.
So we went all the way down to here, and then here, and then here. And finally made it back up to the top. Okay, so that is our depth first search recursively. Does that make sense? And or any other questions on that?
Yeah, it made more sense.
Okay. Awesome. Any other questions that we got?
Could we possibly do maximum depth of binary tree?
Yeah, absolutely.
Dang.
Okay. So let's talk about it first with whiteboarding before we go out and try to code that out. So our maximum depth. So let's pretend that this is my tree. Right? I know it's off screen. This is the tree. And I try to submit this empty null node. What should our answer be?
No.
No?
Well, how deep is this null?
Oh, okay. An empty.
An empty array?
So we're looking for depth. So that's an integer. How deep is this tree?
0.
So would it just be negative infinity?
It's 0, right? There's no tree. That's empty.
That was a trick question.
It's not a trick question. That's very important because that's the base case. The first most important thing is, and what if we pass in nothing? How deep should this be? Next question. This is our node, and we pass in this. What should the depth be?
Should it be 1?
0.
Okay, on the count of 5, write in the chat how deep this tree should be. This A tree. 5, 4, 3, 2, 1. Okay, cool. I'm getting a lot of ones. Thank you, Danny, Doug, Maria, Nelbert, Wagabasi, and Marvin. So see, this still has a depth, right? This just has the depth of 1. But something there does exist.
We have to count like the roots as well.
Yeah, so because we want to count ourselves. It's like if this is very similar to like if we were all in a movie theater and you were in the first row, I would say, hey, what row are you? And you probably wouldn't say 0. You would say, I'm in the first row. I'm in row 1.
Okay.
So quick question, Corey. Mm-hmm. So when we're doing so is this like a DFS? No.
Mm-hmm.
It is. So
very much so.
So with the DFS, are we counting so with this one we're just counting the depth. But with the other problem, we were multiplying the values or something like that. Summing.
We were summing the values of the other one. But this one, we only care about how deep we're going.
Okay.
So, like I guess you could solve this with a breadth first search as well, if you wanted to. But this one really screams nicely for a depth first, because we want to go all the way down to those leaves real quick. And so, okay, so if we agree that this is the depth of 1, and we agree that this is the depth of 0, then given any node, how do we determine A's depth? I have these two. What's the rule?
By its children, right? Or by what its next is, what it's connected to.
Yeah, but what about its children? Let's get really specific. What's the formula? What is A's depth?
1.
Okay, yeah. So maybe that's our time complexity.
What's the
mathematical formula to calculate A's depth?
It'll be like 1 plus the number of children it has, right? Or 1 plus, because A is a depth of 1, and then B is
the depth. So we could say that A's depth is 1 plus its children's depth. Can we agree on that?
Yeah.
1 plus the children's depth is A's depth. So more specifically, since we're looking for the max, right? This can extend out. So it's still 1 plus the children's depth, but we really care about 1 plus max of the children's depth, right? Whoever's longer is whom we care about. Because even if we go back to our first example, or our third example with A and B, A has a depth of 2, even though it's missing a child over here. So if this child, what's the depth of this child?
That's 1, right?
Right now it's 0, right?
Yeah, right? Exactly. So if this pointed to null, this is 0. This is 1 plus 0, 0, we could say, for null, right? So we have the choice of going with B's children or with null's children. So we want to choose this one because it's greater than this side. So we can say 1 plus the max of its 2 children, which is going to be 1. And therefore, this should evaluate to 2. Sorry about that arrow. Okay, so with this in mind, let's try to code something out. So I think this was a practice problem, if I'm not mistaken, which means it should be on my list here. Max depth of tree. Okay, let me share my screen. And we'll go to this leak code problem. Hopefully I haven't solved it so recently that it shows the answer. It does, but that's okay. All right, so let's go ahead and think about this. I'm going to change this because this kind of stuff annoys me sometimes. Okay. Right, so we've got our max depth function, and we've already decided, we've talked about if the fact that there's no root, if there's no root, we said we wanted to return what?
0.
0. Sounds good to me. Otherwise, we want to return whatever is the max of its 2 children plus 1 because this is the depth that we're on. So we can go ahead and return 1 plus whatever is the max. So we'll say math.max of whatever results we get from going down the left side and the right side. So to go down the left side, I'll say max depth of root.left. And to go down the right side, I'll say max depth of root.right. And that should be all I have to do. So let's go ahead and run the code. Passes the first test case. So let's go ahead and submit and see if it passes all the test cases. It does.
All right. So that looked, yeah, that was kind of crazy. So.
But it is what we outlined on the whiteboard, right?
Yes.
What if we don't use math.max?
Okay, I'll address that in a second. I want to let Danny finish his question, and then I'll do that one, okay?
Yeah, so I know it's supposed to look like what we did on the board, but I'm just like, I can't see it.
Okay, well, let's go back to the board real quick. So let's go ahead and look at these tree, our tree that we've been playing with. And I'm going to go ahead and put null here, null here, null here, null here, null here, and null here. Okay, so these all point to null. And we agree that if I pass in this tree or a null tree, we're going to get back 0, right? Because there's no depth.
Yeah.
And we also agree that each node has a depth of 1. Can we agree on that?
Yeah.
Okay. So let's go all the way down and say, so if we had a node here and a node here, and this point it's a null, what would our depth be?
2.
2, right? And so that's because we have our 1 plus whatever's the max depth of these two children. So we would go down the left side and check this one. So its depth is what? We would look at its depth, which is 1, plus the max of its two children. Well, its two children are both 0. So that'd be 1 plus 0. And this would be total of 1. We'd also check on the right side here. And the right side would be 0. So now we're taking our 1 plus the max of its two children, which is going to be our 1. And so we get back our 2. So to walk through on this one, we're saying, all right, we have 13. So this is going to be 1 plus whatever we get from the left side and the right side, whichever one is bigger. So we'll say the max of left or right. But that's function calls. These are function calls. So then our left side is this subtree. And it goes, okay, well, I am 1 plus the max of my two children. So it's going to be max of left and right. So I'm just going to say L and R. And so we're going to go down this one here. So now we're in this subtree. And this subtree's max of its two children, we'll say, is 1, right? 1 plus 0 and 0. So now this gives us back a count of 1. Our right subtree for our 5 is going to look at this subtree, and it's going to look at the max of its two children, which are both 0. So we're just going to get back a 1 here. So these evaluate to 1, and this becomes 2. So the max sub when we call on 2, when we call depth on 5, we have a 2. So our left side here is 2. Now we're going to look at the right side, and we're going to call it on this subtree, and we get our 7. And our 7 looks at its left children and right children. These are both zeros. So it's 1 plus 0. So our right tree is going to be 1 plus 0. And this is going to be right, which is going to be 1. So now our left becomes 2, our right becomes 1. And we're going to say, well, what one's larger of these two? And we're going to say the 2 is larger. So we're going to return 1 plus 2, which gives us back our 3.
Okay. It's like recursion just always throws me for a loop as to how it works. But
recursion always does what?
It throws me for a loop. Like it's like visualizing it just always seems crazy, but I visualized it just now. So essentially all we did was just call left on everything that was on the left, and then once we got everything on the left, we started going back up and checking the rights from the bottom up.
That's right. Yep.
Right.
Started going down the right side then after, and we keep comparing. So it just puts it on a pause.
Yeah. So it stayed in the left for the whole beginning, and then went to the right, and then came back and
then chose the max between those two sides.
Yeah.
Okay. So now to address Maria's question of, let's say we didn't use max.math. So this is the best thing I will say to use and really common in a lot of problems. So like I wouldn't try to hide from this one. But if we wanted to do something else, I could go ahead and say const left depth or something. And I could say max depth. And I could go ahead and run down my left side, root dot left. I could also go ahead and run down my right side. Still got to go down both my sides. And so now I just have to do slightly different logic here. I would have to check which side is larger. So I'd say, hey, if left depth is greater than right depth, I could return my 1 plus left depth. Else, return my 1 plus my right depth. And I believe this will also still work for us. Worked on that one. Let's submit it and see if it works. Still works. So that's how we could do it if we didn't use math.max. We would just have to do a comparison of which side is larger with each one.
I get it now. Thanks, Corey.
Yeah, no problem. Okay. Awesome. Oops. All right. Any other questions here?
Would you mind going over the binary tree level order traversal?
Sure. Let me take a look at what problem this is. Is this part of the practice test?
Yeah.
Yeah.
Send in the chat.
Okay. Let's take a look at this problem. Whoops. Okay. Let's think about it. Const. Okay. So for this one, it says, given a binary tree, return the level order traversal of its nodes, values from left to right, level by level. So for this one, we could keep track of the current level that we're actually on. Okay, so wait, let's see. Somebody's writing something in the chat. I want to make sure I get it. Thank you, Corey. I got what I need. Oh, have a great Sunday. Deja, happy Mother's Day. Okay. So, okay, let's talk about it before we actually code it. Let's talk about it with the whiteboard. So for this problem, we are doing a different kind of traversal. So for this one, we're doing a BFS, right? Breadth first search, which is kind of cool. But
Oh, quick question.
huh?
So why are we doing a breadth first search instead of a depth first search?
Because the question is asking for a level by level.
Okay.
So let's say I'm going to do A, B, C, D, E. Okay, so I've got this following tree. And it says to do level by level. So breadth first search looks at one level, the next level, and then the next level. That's just how it works. That's the point of it. So breadth first search is good for this problem because this problem's asking for levels. It's also good for trying to, like in graphs, usually trying to find like the closest path to things. Often you'll be doing breadth first searches for that kind of stuff. So I should make that clear. DFS and BFS are not specific to trees. You can use those types of traversals on graphs as well. You just have to add a little bit of information on your data to make sure that you check if you've already visited this node or not, just in case things are connected. You don't want to keep checking the same node over and over again, which points to the next node's child, which points to this node's child, which points to this, points to this child, points to this child, points to this child, points to this, and then you'll be in an infinite loop. So you have to keep track of like, if I've already visited this node. Someday, if we have time, we'll go into graphs and stuff too. I think they're kind of cool, but breadth first search is really good for that because you can find the shortest path. Okay, so for this one, it's asking for this multi-dimensional array, and each array is broken up by these levels. So for this one, we could look at this, and we could think of, I have an output array, and I could keep track of these depths. So let's say I'm given A, and the first thing I do is I just give it a depth property of 0. Okay, that's the first thing I could just do. I can just assign it a property, key value pair, right? It's an object, the node. And so I can say, hey, okay, do I have an array at the 0th index of this empty array? And I go, no, I don't. So I go, okay, I'm going to add it at the 0th index and also add the node in here. So I'll say A. Cool. Then I'm going to look at its children. I'm going to push them into the queue. So I've got my queue, and now I'm going to push my B and my C in there. And before I put them in the queue, I'm going to also give these their depth. So I'm going to give them a depth of whatever I am plus 1. So now our depth for B is 1. Our depth for C is 1. Right? So now these both have the C. So now when I dequeue, I go, okay, I've got my B. I'm going to look at its depth, which is 1. And I'm going to see if I have an array at the indice of 1. I don't. So I'm going to make it. And I'm going to put my B in there right away. So I put my B. Okay, great. That's now my output. I'm going to put my depth plus 1 onto my children. So D is going to have a depth of whatever B's depth is plus 1. And E will have whatever B's depth is plus 1. So these will have a depth of 2. And these will be added into the queue. I should have dequeued my B already. So now in the queue, we have C, D, as well as E. Okay? And they have the depths in there. Okay, so now I'm going to dequeue my C, and we've got our C. We look at C's depth, and we see that C's depth is 1. Right? And we go, okay, do I have an index in this array at 1? And I do. I already have an array there. So I'm just going to push it in. So I'm going to add my C, like so. And I'm going to look for its children. It doesn't have any children, so I'm going to move on. I'm going to take my D out. So I dequeue my D. Time to process my D. I'm going to add its depth plus 1 to its children. Doesn't have any children. So No big deal. I'm going to check if depth 2, which is its depth, is in there. It's not, so I'm going to go ahead and add that into our array at the second index. Again with E, DQ the E. Look for its children, doesn't have any, so no big deal. I'm going to look at its depth, which is 2. Do I have an array that's at the index 2? I do, so I'm going to push it in. So I'm going to push my E in, empty it. My Q is now empty, and I can go ahead and return this output array. So that's going to be our overall approach.
So the way that you're like drawing it, so are we actually pushing in, are we actually like adding in an array to an array?
Yes.
Or we are.
Mm-hmm.
Why are we doing, why can't we just add it, like add the nodes to just the entire array?
Cool. So I'm not sure if you've read this problem. This problem specifically is asking for an array of arrays where each internal array represents an entire level.
Oh, okay.
So here, let me share my screen so we can look at that problem. So this is what the output is for this tree.
Okay.
And so because of that, I have to do it that way. If it just wanted one array with everything in order, well, then I would have done it a little bit differently. Does that make sense?
Yeah.
Is that fair? Yeah. So
the output was supposed to be an array of an array.
Got it. Yeah. So this is all about trying to match the output. So for this one, I'm just going to do a quick check. Like, hey, if I don't have a root, what should I return?
An empty array?
Empty array.
Yeah. Sounds good, right? So now I do have a root. So I'm going to make my output. So I'm going to say let output. I'm going to make that. And I'm going to make my queue. Whoops. Let my queue, some weird space. And my queue is going to behave like a queue because this is going to be a breadth first search. And I'm going to start with my root. And right before I put my root in there, I'm going to also add this depth property to my root. So I'm going to say root.depth is going to be 0. So now one of the nodes has this depth property, right? I'm adding this. It doesn't come with it. We see it only comes with the value left and right. So I'm adding a new key. I'm allowed to do that. It is an object. So when in doubt, because sometimes I've run into people that are like, oh, I wish I had a depth property. It's like, well, you can have one, right? As the programmer, you get to decide how things look. That's one of the best parts.
Corey, Corey,
sorry?
I have a question. On line 15, so basically we start with no root. And then in 16, we add the root. Because this is where I get confused. Like when you put like the root that equal to 0.
This is just a key value pair of an object. So I'm giving the root the property depth and giving it at 0 because this is supposed to be in the 0th index at the end of the day. My depth is keeping track of what index I belong to inside of this output.
Okay, so that's why I get confusion when you ask before.
Okay, yeah. No problem. Okay, so then we're going to just do a basic breadth first search. So we'll say, hey, while our queue has a length, we will get our current node. So I'll just say node for now equals queue.shift. And now let's update and mess with its children. Hey now. So we'll say, hey, if our node has a left, so if it's got a left child, we want to say node.left.depth is equal to node.depth plus 1. So we can go ahead and add this node. We also want to add it to our queue. So we'll say q.push node.left. Okay. Now we'll also do the same thing with the right. So we'll say, hey, if node.right, we can add that depth property to the right node. Node.right.depth is equal to node.depth plus 1. And q.push node.right. Cool. So now we've added some things, but we still haven't processed our current node in any way. So now we have our chance. So we can say, hey, if output at node.depth. So if there's something at this current node, so in the array, if we have an element, right, already at this index, then I can just go ahead and say output at node dot depth dot push, and I don't know if it wants values or what. No, if it's nodes values. So we'll say node dot val. Right? Else, in the case that we don't have anything at that index already, we'll say output at node.depth is equal to an array, and we can just put the value straight in there. So that's going to be our first array. At the very end of this whole while loop, we'll just go ahead and return our output. And let's start testing and debugging. I'd be pretty lucky if the whole thing was right on the first type. Okay, well, that one worked. Let's go ahead and submit it. Oh, we are getting lucky. Kick ass. So we didn't have to debug. That's great. But that's all we have to do, right? So it's all about adding the secret to this problem, right? It's pretty much your general breadth first search, just as Q where we're pushing in the children if it has the children. The only difference is two things, right? One is we're adding a depth property, and we're adding that property to its children as well. And then we also have our processing step. And our processing step is just updating our output in some way. It's saying, hey, do I have an array at this index of depth? If I do, I'm going to push in my new value into it. Otherwise, I'm going to create a new empty array with that value inside of it at that depth index. Doug, does that help?
Yes.
Awesome.
The depth was giving me an issue, but I think I know how to solve it now.
Sick.
So so where are we actually creating the new array that gets pushed into there?
Well, we're not pushing in a new array. We have our output array, and I'll split it up a little. Here, we're seeing if there's anything already at that index to go ahead and push the node value into that array at that index. Otherwise, at that index, we're going to assign that to be an array with the value inside of it.
Okay, yeah, that's what I was looking for.
Okay.
Thank you.
Yeah, no problem. Any other questions on this one?
We did this one a little different earlier today. Like we
Okay.
used the while loop and also a for loop in there. But that would make it that would mess up the time complexity.
Did it work on LeetCode?
No, did it work?
Yes, it did work. Yeah, I try it.
Okay. I know it definitely worked on VS Code and on REPL.
Yeah, but that's not the same test cases. Can maybe somebody can show me so we can talk about it?
Ashia or D or somebody? Okay, I'll pull up my screen.
Okay, awesome. Okay, cool. Okay. So this one, let's take a look. We've got if there's no root, return output. Cool. Q. Okay, so far very similar. Then we've got let level is equal to this empty array. And size is equal to our q dot length. So whatever the size of our q is. Interesting. For let I is equal to I less than size. Current dot shift level dot push current dot val. Cool. Yeah, that worked. That's cool. So yeah, I don't think that damages our time complexity or anything. It's just how does this work? Oh man, this is hard. This is a little harder for me to get my mind around, but it's cool. So you would be shifting from your Q, but because your Q size isn't changing, right? So it's already made once.
Mhm.
And then you're iterating that many times. Yeah, that's cool.
Okay,
Yeah,
awesome. Thanks, Corey.
sick.
But it didn't work on LeetCode, so
It did or didn't?
it did not. Or Siham said it did, but it worked for her, but not for me.
Can we try it?
Siham, you want to share your thing? Or do you want me to put this on the LeetCode?
Yeah, just copy it. Let's try it. From yeah.
Right here?
Yeah, I mean yeah, I guess if it's called that, yeah, you should be fine.
Okay. So
Is it the one beside it in the tab?
let me see.
No. Oh, it is. Maybe it is. Yeah.
Okay. Okay.
So our issue is we're calling it the wrong name. We need to call it level order.
Oh, okay.
Okay, let's see.
Cool.
So it works for this one.
Oh,
Yeah.
awesome. Cool. Thanks,
Yeah,
Corey.
that's I didn't do anything. That's cool. That's a cool solution.
Awesome.
Yeah, hadn't thought about it that way. Nice.
Okay. I'm going to stop sharing.
Yeah, sure. Thanks for sharing that, though. That's really cool.
Yeah, cool. Thank you.
All right. Any other questions
So with the in order traversal, is that so you said being that it asked for level order, that's why we did breath first.
Yep.
So with in order, would we still do breath first?
No.
That would be depth.
Yes. So in order, pre-order, order, post-order, those are all referring to different types of depth first searches. The only difference between them all is where you decide to process your current node. If you decide to process your current node before the children, you're doing pre-order. If you decide to process your current node between the children, you're doing in order. If you decide to process your current node after you've processed the children, then you're doing post order. That's all.
Okay. Okay.
They're a little bit less exciting just because it's just a matter of where you want to do it, which it does have its things. Like if you had a reverse Polish notation tree that represents like a calculator, that's essentially, I think that's a post order traversal and things like that. It doesn't matter, but sometimes it will be important for the problem to recognize which one, but a lot of the time it doesn't matter.
Also, you said that with the sorting, we didn't actually have to sort. We just have to recognize the sort, the type of sorts.
You will have to recognize from a picture those which four sorts is which.
Okay.
Yeah, but you won't be expected to implement the sorts.
Okay.
As much as fun as they are to write, we're not going to expect that.
We have to know how to do like the tree nodes and all of that. Like
how
build a tree
to
node.
make the classes with all the tree nodes?
Yeah, like do we have to do that, or will that be provided for us already?
That should be provided for you.
Awesome, thank you.
It's good to know how to do all. Of course, keep in mind all these questions, right? I'm giving you an answer to what is in relationship to the test. Keep in mind, everything is good to know how to do outside of the test as you continue to build things and want to interview and all of that, right?
So it's primarily like traversals and like those sorts of things, like working with these linked lists and trees that we're pretty much being evaluated on.
I missed the first half of that, Marvin. Sorry.
Oh no, like since we're not like going to have to be implementing like the sorts and stuff like that, it's just recognizing the sorts and utilizing different types of traversals and searches.
Yep.
That's what the main evaluation portion of this test is going to be on, right?
Well, it's not. I mean, just the little bit of trees is just a couple questions, right? There's a linked list, a recursive, a binary.
Yeah.
All a stack and a queue, all the types of
a few different
types of questions. Yeah.
Okay, cool.
Right. And now I do recommend, like, after the DSA, to continue studying by like implementing your own classes of these things, right? Make your own linked list class, make your own binary tree. 我不知道。Okay. Any other questions? Anything else anyone needs me to review on this optional review day? Anything at all?
As long as we know how to do every question on the practice test, we should be good.
Yeah, I would think so.
So you're not giving us any trick questions or anything like that?
Not that I'm aware of.
Question.
Corey, for the like knowing the different sorts, you said it's just gonna be like a visual thing, and you would just have to be able to tell like what sort it is.
Yeah.
Okay.
Question. So like, is the test on LeetCode or is it on like a local environment? Because LeetCode is a little bit different than local environments. So I'm just wondering.
It would be on a local environment. Yeah, you will not be able to use any notes
Okay.
or anything, right? I mean, that's the idea. Obviously, people could cheat, right? But please don't, because you're giving yourself a disservice of like an accurate representation of where you're at. Like, there's just no point, really, because like there's no like real grades in that sense. Like, you don't get an A and like way to go. Like, it doesn't count for anything. You just actually have to know the stuff. So if everybody fails one question, that gives me like oh, okay, we got to go over this some more. We got to practice this some more. If everybody passes everything because they cheated or something, then it's like, oh, all right, I guess we're all perfect. And then I won't be able to assist you in the way, right? So yeah, so it's a closed book, but it will be like one of like, I think like kind of like the Unit 1 test or something where you forked it. You can go through problems. I think there's going to be tests associated with it, so you can run those tests. Of course, again, like you should be able to see those tests, but you wouldn't want to code it like, hey, if my input is 12, return 14, and if my input is 9, return 6. And, like, you want to still, like, I'll be checking that. But
So
yeah.
also, just I guess like a suggestion. Like for me, like what helps me is understanding like where we would actually like have these like issues and like apply them in like a real life situation. So if it's like, I know you brought up like searching and things like that, and why we would pick certain types of searches and sorting things a certain type of a way, because like I like to apply it and I like to think about it in like real life instead of thinking like of n and what's n and n minus one, and it's just I don't know, just my brain starts
Yeah.
going.
Yeah, definitely. So anywhere you can think of how to apply something in real life, it is helpful. At the end, you'll be using these directly, like these type of problems, because like some of these problems, you wouldn't use this in real life. You wouldn't have to solve this specific problem, right? But like, it's the familiarity with different data structures that does solve a lot of different problems. And why that's important is, yeah, it happens a lot in real life. But also it's really what you need for whiteboarding interviews. Someone's going to come along someday, I guarantee it. If you apply to jobs, they're going to ask you these types of problems. And that's how you'll get or not get the job to some extent. It doesn't all ride on just the whiteboarding and whether or not you can get it. You know, it depends on how well you can communicate, your thought process, and all of that. But like, that's where these problems really play. I know that's kind of like shitty because you're like, well, how could, like, why do I have to recursively, decide if a string is a palindrome? You're like, why do I have to do that? And it's like, well, because that just shows your mastery of string manipulation and recursion. It's not really like you would have to do that in real life. In real life, you probably just split it, reverse it, join it, and check if it's the same thing, right? But and the really cool examples come with way more complicated data structures, kind of more uses. Like, it's all about graphs. And like, you know, you're thinking of like when you're buying an airline ticket and you want to go from New York to Oregon, right? And different flights cost different amount of money, and there's different opportunities for different layovers along the thing, and there's also a time, right? And all of those are different weighted properties. So to find the most efficient way to get from New York to Oregon with the least amount of money and also the least amount of transfers in the fastest amount of time that's acceptable, that's all like really complicated graphing problems. right? So like, and these things show up, they're like everything, your browser history, that's like a couple different stacks. Like where you're going, every time you're on one, you're going there, and then you hit the back button, and that pops off into the forwarding stack, and you go back again, and then you go forward. Like that's where stack is being used. LRU cache is like where things are really getting used, like all your gaming and all of that. And that's a mixture of a doubly linked list with an object and a hash map.
Sounds super crazy.
So things start to get really crazy. So these are just the building blocks to someday get to those, if that makes sense. Like you're not really going to have to do a breadth first search of a binary tree, most likely for most case scenarios. But you will have to do a breadth first search to find all of someone's suggested friends, or the shortest distance between two words that are real words in a graph, or things like that. The problems get more complicated the more experienced you get. Or so I'm told. I'm still not doing that kind of plain stuff. Forget that.
And also a quick question about the authentication. So is that like actually secure? Because I think I asked you that already, but like, is it really secure? Like, would you be able to make a secure website with like credit card information and everything?
Well, you would never store credit card information into your database.
Okay, passwords, actual passwords.
Well, yeah, so that one's all being stored via Firebase.
So what if somebody gets your account? It's over?
Well, how would they get in your account?
I'm just trying to figure out.
You don't push the keys. You keep your account private.
I feel like our key was being pushed and shown. We didn't hide it correctly.
Yeah, I saw that. I think that was an error from like before it worked.
Okay.
But, I mean, if you're really interested in security, like dive deeper, right? There are platforms and things where like there are no passwords. You just put in your email and then you get a text message. Or you,
so the crypto guy was talking about it.
Right, or you just put in your phone number or something. Like that's kind of the future, maybe.
Yeah, I think I like that.
There's a lot of security stuff, but yeah, these auth. I mean, this is good. You could definitely make a website that has pretty good auth.
Okay.
And you can use OAuth as well. That's like how you can sign up with your Google account and Facebook's accounts and things like that.
So when you're hosting something, essentially, being that you created those environment variables and all that, when you actually go to host it, essentially those variables won't be like shown.
Right.
Okay.
Are we gonna go into graphs?
Possibly at some point. Yeah, I think that's like extended material stuff. So at some point, I think that'd be cool.
Cool.
That'd be fun.
That's basically like network structure in a way.
Yeah, it's just like this big network. So I'll show you kind of. So like,
what are graphs used for?
Everything.
Huh?
Connecting everything. There's all these different types of graphs, like friend networks you could think of. So we got A, and there's directional graphs, and there's unidirectional or bilateral graphs and all that. So like we have B here, right? Maybe we have a C here. A connects to C. Maybe we have a D here, which connects to A, which connects to C. Like this is a graph. And maybe we want to find the shortest path to get from A to D or from B to D, or, I mean, this is kind of like a silly graph. right? But and some graphs have directions. So only D likes A, right? This is like as if we were following on Twitter. So only D follows A, and A follows C, and C follows A. And D follows C, and B follows A. So you can see everybody follows A. So you know that A is now the most important person, right? Well, C might have some like interesting people too, while like B and D are just like nobody follows them. There's no relationships for that. So like there are things to like see, like who am I paying to be my influencer on Instagram? Well, I'm paying A. A is going to be my influencer because everybody follows A. Why would I pay D? Nobody follows D. And so there are like traversals, but even if we just take away the direction parts, and then this is more of like replicating Facebook friends, although I'm sure Facebook weights its friendships based off of how interactive they are with certain people. But without that, we can like, let's say we start with the D node and we want to say like, how do we get to B? Let's put another node in here. That's like F. Right, so now we can look and we look at these children. And like, let's say we were doing a breadth first search again with D, right? So D's children get added, like this is D's not B. And so D gets processed and we're gonna pass in its children of A and C, let's say. And we can be passing weights along the way. So this is, let's say 0. This has a weight of 1. This has a weight of this would also have a weight of 1. I'm sorry. Actually, let me remake this graph. I want to remake this graph. Sorry. This will be better. A, B, C, D. Okay. E. Okay, let's say this is our graph. And we want to find how to get from E to D. By the way, if this isn't interesting to you, you totally don't have to stay. Remember, this is optional. This is for Nover's question, right? I'm going to give E my weight of 0. I'm going to look at its children in the queue, right? So I'm going to add a 1 to my A and a 1 to my C, right? And I've got my A and my C here. I'm also going to make sure that they know that they're visited and all that. See you, Marvin. Now I'm going to look at A's children, and I'm going to look at E, because E's a child of A as well. But E's already been visited, so I'm not going to put it in. I'm going to look at D, so I'm going to pass in, well, I've already found D, so we'll say that's 2. And I'll keep track of D, so I have D now, like I own it. And I'll go out and I'll look at A's children here, and this will be 2. This is the distance from E. Okay, and that now I'll pass my B in here. So now I'll take my, and I've already taken A out. So now I've got C, and I'll look at C's children, and I'll look at E. E's already been visited. I'll look at B. Now B has been visited as well, and this is going to be already 2. So B's, I'm not moving on, and that's all of C's children. I'm going to look at B's children, and B has a child of A, which has already been visited, but also it's important to note that A's value is 1 here, and B's value is 2, 2 away from our starter, right? So we want to keep this at 1 instead of incrementing it to 3, because we're looking for shortest distance. B's child is 1, so we don't want to change that. And then we're done with that, and we have our B. So now from our D, we can traverse backwards, going the shortest way. So we go from our D to our A, and now our A can decide if it wants to go to 2 or to 0, and it goes to the 0. So we know the shortest path from E to D is DAE, or reversed. Does that make sense, Nova?
Yeah, it's really cool.
Yeah, so that's like kind of like graph stuff that we can get into at some point, but it's kind of cool. There's some cool graph things.
So, quick question.
Yeah.
Where, like, so with all the DSA stuff, where would we actually apply it in our application? Does that, like, so if we're in the back end, do we send a query for what we want, get what we want, keep it in the back end, do some DSA stuff, then send back something specific to the front end?
Yeah, we could do that.
But we would never do that in the front end. We would never like just send everything to the front end.
Probably not. No, it's it's usually really expensive.
Okay, what do you mean by expensive?
It's a lot of data that we'd have to send in, so that could take a long time to bring that to the front end.
Okay.
And once we're in the back end, all the data is like right there for us.
Okay.
See you, Kevin.
All right.
See you, Kong.
Well, I'm about to start working on, or try to finish working on these problems. Are you going to be around till 6, or you out of here?
No, I have to work today, so I'm still around.
All right.
Yeah. See ya.
Thank you.
You're welcome. If anybody else has any questions, I am here.
Oh, wait, one quick question, not related to this.
Okay.
I came across GitHub for like students in education. Do we have access to that? Do you know?
I don't know anything about this. Let's take a look.
I just sent you the